What's up, guys? It's Andy, and today we're going to figure out the area under a graph. And you're probably thinking, well, how do we do this? It's not quite easy. I mean, if you gave me a linear graph, then it would be pretty easy. You could just break it up into like a triangle, and then you'd figure out the area of the triangle, and you would be all set. You'd be on your way. But no, I gave you a curve. As a matter of fact, it's this curve right here, negative x minus 3 squared plus 9, and I'm asking you to find the area. So you're probably like, is there some special formula? Well, we'll get to that, but for now, think of a way that we can find the area of this thing. And the best way that I came up with is to divide it into rectangles. So I broke it up into these rectangles of equal width, and for each one we're just finding f of x for each one, and then we're doing the area formula for a rectangle, which is area equals base times height, and we're adding it all up, so it looks a little bit like the summation of x equals 0 to 6 of y times the change in x, which is just 1 in this case. So here, that's 5 times 1 plus 8 times 1 plus 9 times 1 plus 8 times 1 plus 5 times 1. And let's see, that gives us 35 roughly. And that's pretty good, but there's an issue with this. Over here, we're going a little bit past the curve. I know I drew this by hand and it doesn't look so great, but there are these areas where we're not accounting for it, or we're either over accounting for it. So like, right there, for example, we're going beyond the bounds of the curve. And so you're probably thinking, well, what's the best way to solve this? Well, we can just make the change in x less. So, we can, make it like half. But this isn't drawn very well at all. I'll be the first to admit I've got very poor drawing skills. But, even at a half, we're still running into these issues, They're like little gaps right there and stuff. And you're probably wondering, well, this is calculus. This is all about infinity, curves, and stuff like that. So, are we going to infinity? And yeah, the short answer is yes. We're going to infinity to get the best approximation. And that's roughly the formula that we come up with when trying to figure out the area of negative x minus 3 squared plus 9 right here. So it's a sum, or it's actually the limit as t goes to infinity of the sum from n equal to 0 to t of f of t over 6, or actually that's supposed to be 6 over t, because we're trying to get up to 6 in infinitely small increments, and delta x, which is going to be roughly 1 over infinity, infinitely small. And this is actually something called a Riemann sum. You're summing up a bunch of things to figure out the area under a curve. And you're probably thinking, well, you got a limit in there, but this doesn't exactly relate to anything that we were doing. But we've never seen anything like this. Except you have. Delta x is the same as dx. And you got a function right here. So that's function times dx. And now you're like, oh, I get it. I've seen it somewhere before. That's right. The way to find an area under a curve is by integrating it. And this time we got some letters out front. This just means after you do the indefinite integral, which just means integrate like normally, you plug in b. So, let's just call the antiderivative capital F. So you do f of b minus f of a. And that gives you the area under the curve. Because it's a short video today, I just want to explain why this works. So why does the integral actually work for the area? Well, let's say we got this graph here. We've got this function right here, f of x, and there's 0 right there. We got some value x right here. And then we got something called x plus h right here. And we want to find this area right here, the green area. And We want that area right there. And it's h units wide, so there's h between there and there. And we have a lower and an upper estimate for the area. Because if we go back to the rectangle formula, a equals base height, we can say that, I think I drew it down here, our upper estimate would be h times f of x plus h. That gives us the upper estimate, this big triangle right here. And then we've got a lower estimate, which is just f of x times h, which is this lower triangle right here. And the actual area that we're trying to find is this little, not exactly, weird curvy shape thing. Yeah, that sounds about right. So we can plug that in. We figure out the area for the lower one is f of x times h, and the area for the upper one is f of x plus h times h. And let's say that we've already got an area function. You know, we'll call it a of x. And from from x plus h to x, the area would be a of x plus h minus a of x. Because we're actually, I forgot to mention, a of x calculates the area from 0 to said point. So it would be a of x plus h minus a of x. And we know that it's going to be between our lower and upper estimates. So we know that f of x is greater than or equal to less than or equal to a x plus h minus a of x, which is going to be less than or equal to h f of x plus h. And to simplify this, why don't we divide by h? So we get f of x less than or equal to a x plus h minus a x over h less than or equal to f of x plus h. And if we take the limit of this inequality as h goes to 0, we're going to notice something. That's a derivative right there. Oh, why is that yellow? Yeah, that's a derivative right there. And, you know, limit as h goes to 0 of f of x, well, that's just going to be f of x. That h is going to simply disappear, so we're going to have f of x on both sides, but we can just say that this is derivative of a with respect to x, or dA dx, and that's going to end up being equal to f of x. So we know that the derivative of the area with respect to x is going to be f of x. Conversely, this means that if we integrate f of x dx, then it's going to be that area function. So that's the basic proof behind, you know, integrals being the area function. We start off with some triangle thing, we set the bounds, then we realize, well, if we take the derivative of the area function, it's going to be equal to the original function. And that's all I got for you today. It was a pretty short episode. Tomorrow we'll be figuring out the area under the curve and actually figuring out what that area is instead of just doing this conceptual work. So until then, stay tuned, peace out, be good, study.